So, we have been studying this light. So, what is light? And main purpose is to that when there is a interaction between light and matter, then how does that light behaves? Because we need to understand that one, otherwise we cannot understand that interaction outcome, which is a spectrum. So, light is usually explained by the classical electromagnetic theory, and which is good enough to explain say phenomenon like a reflection, diffraction, interference and also on. But there was a experiment that black body radiation, and people found that that is not being explained by the classical electromagnetic theory. What is this experiment that we will discuss? So, in black body radiation experiment, in radiation that one, what is black body? Black body is a object that absorbs all kinds of radiation, and when it is heated that emits all kinds of radiation back. So, now the physicist Lord Rayleigh from a classical viewpoint used this equipartition principle and derived Rayleigh-Jeans law. What is this law? This is the density of energy, dE, difference of energy, density of energy is difference of lambda. So, where the density which is known as the rho, which is used as a rho symbol, is given by this one 8 pi k T by lambda to the power 4, and where k is the Boltzmann constant. So, what it says that when you go to the lower wavelength or higher frequency, then this energy distribution density of states rho should be increasing, because lambda is more in this equation, lambda is more, lambda to the power 4. So, it is exponentially increasing when lambda is smaller, smaller increasing. That pink color, this violet color, it shows this one. In this way, so if you decrease the wavelength, then since it is in lambda to the power 4, so there should be a huge increase, that is called UV catastrophe. So, that should be, so this violet color, it should go exponentially in the shorter wavelength region. Now, but we have seen that in classical electromagnetic theory, when you consider it, then this theory says that at the shorter wavelength region or higher frequency region, following the Rayleigh-Jeans law, it should be a huge output of the energy. But when you do the experiment, then you see this color, that bluish color, this color. So, it goes and then again it decreases. So, that means that whatever the Rayleigh-Jeans law predicts, that UV catastrophe is actually not true. Experimental observation says that it will decrease after certain wavelength. Then German physicist Max Planck studied the black body radiation from the viewpoint of thermodynamics, and contrary to the classical theory, he proposed that the energy of each electromagnetic oscillator is limited to discrete values. So, this discrete values is important. So, this is the limited to discrete values and cannot be varied arbitrarily. So, there the quantization of energy concept came. So, E is equal to n h nu. So, it is not a continuous as it was thought. So, he gave a revised equation dE is equal to rho del d lambda, and where this rho, density of states, rho is 8 pi AC and lambda to the power 5 instead of 4, and there is a term, exponential term, e to the power AC by lambda kt minus 1. And from there only this h value came, this Planck constant. And there if you check that at shorter wavelength, say like nu lambda is close to 0, in that case rho becomes close to 0. So, at shorter wavelength region this become close to 0. So, hence the energy density approach 0 at higher frequency in that is in agreement with the observation. So, this is not considering the classical approach, he could analyze that observation, black body radiation observation. Now, another that is the we are now trying to understand that how to explain the light. So, another experiment or experimental observation that shows that light cannot be explained as a just a wave, and that one is emission spectrum or absorption spectrum. So, this is the emission spectrum. So, this is the emission spectrum of iron, excited iron. So, you see these lines are discrete. So, you see a discrete line. Similarly, in some of the absorption spectrums, particularly in gas phase, there also you see the discrete lines, like here absorption spectrum of SO2 molecule in this UV region. So, this is a compelling evidence that quantization of energy in spectroscopy, the detection analysis of the electron radiation absorbed or emitted or scattered by a substance. From the emission absorption spectrum is both the radiation is emitted or absorbed at a series of discrete frequency. These are the discrete frequency. Okay. So, this observation can be understood if the energy of the atoms or molecule can also confined to discrete values, for then energy can be emitted or absorbed only in a discrete amounts. So, what it says is that can be understood with this one. So, this energy levels should be a discrete value like E1 and then E2 and then E3, not in between anything. So, and when we are thinking of a process, say emission process, so from E2 it is coming to the E1, from E2 it comes to the E1, then that energy that will be released from the or light that will be released from the system, that will be the difference of E2 minus E1. So, the h nu what we will observe is E2 minus E1. So, this is a discrete one. Similarly, if we try to observe a emission from E3 to E1 and E3 to E1, so that emission will be h nu will be E3 minus E1, E3 minus E1. So, this is the. Now, you see this frequency is more because the difference is more high energy. So, this radiation that we are seeing having a higher frequency than this one. Now, if you think of a emission from E3 to E1 that is given by this one. So, from here to here. So, the radiation you will see is h nu is equal to E3 minus E2, and this is a lower energy difference, the difference is low between these. So, the frequency will be low. Now, let us understand the system more through a few numericals. So, first one is that calculate the number of photons emitted by 100-watt yellow lamp that we see in tungsten lamp in 1 second. This example I have given just to have an idea how many photons we get actually from the light. So, just a 100-watt bulb, and you are trying to understand how many photons it gives in 1 second, and take the wavelength of the, you need the wavelength say in visible region 560 nanometer, and assuming it is 100% efficient. And then you can use the same formula that we have shown, and then if you use that formula, the final data is interesting, that it gives 10 to the power 20 photons. It gives 10 to the power 20 photons of say 560 nanometer in 1 second. In 1 second, so many photons it gives. Now, what we understood is that light cannot be explained as a simple wave, and light also cannot be explained as a simple particle. So, the inability of the wave model to explain the blackbody radiation. Wave model cannot explain, as we have seen that blackbody radiation, that Rayleigh-Jeans model cannot explain the blackbody radiation, particularly this high frequency region where we are expecting a UV catastrophe considering the wave equation, wave consideration. So, the atomic and molecular spectrum also it shows that it cannot be explained by the continuous wave. So, there is a necessity for looking into the light in a different aspect. So, that then comes the wave particle duality, when somebody is saying that light has both wave and particle duality, and that person was de-Broglie. So, what are the things we have so far seen, that if it is light is considered as a just pure wave, then it is fine with the explanation of interference and diffraction, reflection or refraction. This can be explained well if you consider light is a pure wave. But what about but it cannot explain the blackbody radiation that we have discussed, as well as atomic and molecular spectrum, which needs a discrete model. On the other hand, so if you consider light is a pure particle, then interference, diffraction, those needs wave nature. So, those cannot be explained, but other things can be explained. Then the wave particle duality has come. So, few early experiments we will be discussing, which shows that wave particle duality is really the light's property. So, we will be discussing two things. One is the famous Einstein's experiment, this photoelectric effect, and another one is the Davison Garmer experiment. First one is that it should have a particle nature, and the second one that it should have a wave nature. So, this is in the 1927, this Davison and Garmer, two scientists, they worked. Actually, their work was a kind of serendipity. Suddenly, they saw this one, because the metal surface they are using, it changed because of the heat. You can study their details. I will not be talking about the details, but you can study. So, now we will be studying the photoelectric effect. So, now photoelectric effect is that when a radiation falls on this surface, then sometime this it ejects a electron, and the electron has a kinetic energy and it goes away. Sometime you apply the radiation, but nothing happens. So, that Einstein has given a formulation to that. What he observed is that the light must behave as a photon, as a particle, that means photon, to kick out this electron from the surface of the metal, and no electrons are ejected unless the incident light has a sufficiently high frequency than the threshold value for that metal which holds the electron. So, intensity is not a matter, it is a frequency. So, he said that threshold frequency, the few characteristic is the threshold frequency, that electrons are emitted only if the radiation means this incoming radiation falling on the surface, the radiation frequency is above a certain limit, and that depends on the material to material, that is called threshold frequency. If this frequency is above that frequency, above that limit, then it can kick out a electron, otherwise not. Now, another point is that what about this kicked out electron, that kinetic energy, okay, that will move with a kinetic energy. The kinetic energy of the emitted electron increases linearly with the frequency of the incident light. So, if you give more frequency, then it is run away with higher velocity. And then instantaneous emission, electron emission occurs immediately above the threshold frequency, even at low intensity. So, this one Einstein gave a formulation, and the formulation is very simple formulation. It is the kinetic energy of the kicked out electron is equal to the difference between the this light energy that is given, light frequency that is given, minus the holding power of the metal, which is called this threshold, which is called work function. Okay. So, this the photon energy is this one photon energy, and the photons overcome the metals work function is phi, metals work function. What this equation is easy to remember in the sense that you have a term, this is property of the metal, how strongly it is holding the electron, and this is the light, what frequency of light you are giving. So, if this one is more than the holding power of the metal, then electron will be ejecting out. When electron ejects out, what will be the kinetic energy? That is given by this. So, difference of this will be the kinetic energy of the emitted electron. So, half the mass of electron, half mv square. So, half mv square is h nu minus this phi, that is the holding power of the electron, which is known as metal's work function. So, when this is more, that means electron will be ejected with certain kinetic energy. When this is low, this light is low, if it is lower than the metal work function phi, then what will happen? Nothing, it will not eject. So, that low frequency light cannot do anything. Now, this can be understood here in this one. You see that you have two A and B, and in A it is shown that say this is the work function. So, this is the work function. So, energy, that means this is the minimum energy you need to give to kick out a electron from the metal, that is phi, and you are giving your that whatever light you are using, that frequency is this one, this is the frequency of this. So, this is smaller than this is the energy required this one. So, according to this one, this Einstein, there is nothing is going to happen. So, nothing will happen. Okay. Now, another scenario. What is that another scenario? Your work function is the same work function. So, this is the minimum energy required to take out the electron from the metal surface. And how much energy you are giving? You are giving this much energy, much more than the necessary one. So, now in this scenario what will happen? In this case, this light will be able to kick out the electron from the metal surface. Now, if it able to kick out the electron from the metal surface, what will happen to the electron? Electron will be ejected with a kinetic energy. How much is the kinetic energy? This difference. This will be the kinetic energy of the electron. Okay. This is half m v square. So, this will be the kinetic energy of the electron. So, these things I have taken from the Atkins books, is nicely explained. Now, let us go through a few example. So, say this work function of the metallic cesium is 2.14 eV work function. So, work function means this is the theta. How much it is? This theta is 2.14, okay, eV. Remember, you have to convert it to joule because all things are happening in joule here. So, and calculate the kinetic energy and the speed of the ejected electrons. when you are using two types of radiation. One is 700 nanometer radiation, another is 300 nanometer radiation. So, the purpose of this one to tell you that when you use a low energy light, that is 700 nanometer light, what happens when you shine a metal, particular metal whose work function is say 2.14 eV. When you shine 700 nanometer on that metal surface, what is happening, and when you shine high energy 300 nanometer light on the same metal surface, what is happening. So, that is what the this photoelectron effect of Einstein's. So, first what you have to do, you have to convert this 2.14 in joule. So, the work function of this metal is cesium. Cesium is 2.14. So, you have to convert the unit. So, work function of this one is 3.4 into 10 to the power minus 19 joule. Okay. And the rest of the things you know, rest of the things this Planck constant, speed of light, mass of electron. So, now you know this energy of photon h nu, and then since your wavelengths are given. So, h nu, as I said, nu lambda is c. So, nu is equal to c by lambda. So, you have to transfer it to h c by lambda, and the kinetic energy as you have seen, half mv square is equal to E is the light energy minus work function, that is already you have shown. Okay. So, now what you have to do is that once you put 700 nanometer in this lambda and work function is same, you have to once you put 700 nanometer in this function, in this equation, whatever E minus this phi, this one. How much comes for 700 nanometer? Doing the same thing, it comes minus kinetic energy is minus 0.59. So, kinetic energy minus has no meaning. So, that means what does it mean? Physical meaning is that no electron will be ejected. That means, if you give 700 nanometer light on a cesium whose work function value is 2.14 eV, nothing will happen, no electron will be ejected. Okay. Now, what will happen if you put 300 nanometer, if you shine the metal cesium metal with a 300 nanometer light, what happens? So, you do this, now you have to put in this lambda 300 nanometer. So, lambda 300 nanometer, and you calculate the energy of the light, it comes at around 6.6 into minus 19 joule. So, now you have to the kinetic energy is E minus this. So, this minus this. So, you have 3.19 into 10 to the power minus 19 joule. So, if you if you use this one to get the kinetic energy, then the velocity of the light, velocity of the electron, ejected electron will be, this is a positive quantity. So, that means this electron will be ejected and its energy will be 3.19 due to 10 to the minus 19, but it is asking for the velocity, speed. So, you have to convert into speed, and then it says that 8.37 into 10 to the minus 10 to the power 5 meter per second. So, that will be ejected with a speed of 10 to the power 5 meter per second, so fast. So, what it says that Einstein photoelectron effect is correct if it needs a particular frequency which is more than the threshold of the metal threshold for the ejection of the electron from the metal surface. If it is more than that, then it will eject. If it is less than that, it will not do anything. So, less than that is 700 nanometer is less energy light. So, nothing is happening, and if you give 300 nanometer, yes, electron is ejecting and its velocity will be 10 to the 5 meter per second. So, this is a good example to understand the photoelectric effect. Now, another experiment that Davison and Garmer did, it shows that wave nature of the particle. So, what they have actually done, they have actually shined a nickel crystal, polycrystal, nickel polycrystal with electron beam. So, electron beam, you know, the electron beam should be particle, bombarding with a particle, but they have seen a wave character of the diffracted electron. So, this is very interesting, and then that is because this it is a serendipity, suddenly they have observed. So, when they are bombarding this electron, this nickel crystal, polycrystal, there was a heat due to heating effect that it became a kind of grating, and then it's this electron beam is getting diffracted as a wave. So, wave can be of two types. So, it can be a constructive one, it can be a destructive one. Like in this case, it has shown that two waves, these are two blue waves. If they are in a phase matching condition, they should be constructive. So, together will give you the stronger one, together is giving the stronger one. But if it is a destructive interference, then this, like, one wave is this one, another wave is this one, they are opposite of the phase, then the product will be destructive one. So, this shows that particle behaves as a wave, electron beam. Now, together this de-Broglie hypothesis, he has presented the de-Broglie hypothesis. He has presented that any particle with a momentum of p has an associated wavelength, means particle will have a wave nature, wave will have a particle nature. So, what is that? That any particle with a momentum p has a associated wavelength. So, lambda is equal to h by p, lambda is the wavelength of that. So, for larger objects like a steel ball or cricket ball or tennis ball, the momentum is so high, this one is so high, say for cricket ball is so high, the lambda will be very small to observe. But electron, in case of electron, neutron, their mass is very low. So, you can observe the lambda. That also I have a example to show that if the mass of a if you think of studying this one, if the mass is high, then this lambda will be very small. If the mass is low, lambda will be reasonable to observe. So, in modern application, what is that? Establish that all particles including electron exhibits both wave and particle properties. So, that is finally known as wave particle duality. Showed that the energies of electromagnetic radiation and particles are quantized at a smaller scale, necessitated a new framework, quantum mechanics, replacing classical theory for small scale phenomenon. So, let us see one small example, this one. So, now it says that estimate the wavelength of electron. Now, we are thinking of small particle. So, that has been accelerated from a rest through a potential difference of 40 kilovolt. So, what will be the wavelength? Electron is a particle. So, what will be the wavelength of that, considering the de-Broglie equation? So, the wavelength will be of 1.6 into 10 to the minus 12 meter. That means it belongs to the gamma radiation. Okay. So, it belongs to the gamma radiation. So, this electron will behave like a gamma radiation. Now, another one is that this is the interesting one. So, you have two things, one is that a tennis ball, another is the neutron. So, what will be the wavelength of the neutron? What is the wavelength of the tennis ball? Because according to the dual nature, so tennis ball will have associated wavelength, neutron will have associated wavelength. So, what is the associated wavelength with neutron? So, let us calculate this one. So, associated wavelength with the neutron at 300 of course temperature. So, neutron mass you know, so it is given here, temperature is given here, Boltzmann constant. So, kinetic energy you can calculate, and the momentum rho, and according to de-Broglie equation you put that lambda is equal to h by rho. So, you have now h, you have now rho because you calculated the rho, and then you see it is 177.9 picometer. So, 177.9 picometer can be detected by the detector available with us. Now, what about the tennis ball? So, what is the change in the temperature will be the same, change is the mass, whereas the neutron mass was 10 to the minus 27 kg, and in this case mass is 0.027 kg, so heavy. So, this 10 to the power minus 27 and this is 10 to the power minus 2, okay. And the speed is given that say like a tennis ball, when somebody serve, that is 80 kilometer per hour. So, this one the speed is 80 kilometer per hour, you have to take this unit has to be always considered, meter per second you considered, and then you calculate the first momentum is mv, calculate momentum, this is 1.267 kg per meter, and then use de-Broglie equation. De-Broglie equation is lambda is equal to h by p, this is a momentum, this is a h Planck constant. So, if you put this one, then it comes 5 into 2.3, 5.223 into 10 to the power minus 34, 10 to the power minus 34 meter. It is very small, that means this wavelength is very small. So, that kind of small wavelength we cannot detect. So, this tennis ball, when there is a tennis is being played, the tennis ball is also, this is a particle, but it is associated with a wave, and the wavelength associated is 10 to the minus 34 meter. So, it is so small that it is associated, but we cannot detect. Okay. So, what we learned so far is that light exhibits both wave-like and particle-like properties. Depending on the type of the experiment, one can identify. The photoelectric effect demonstrates that light energy is quantized into the photons. Only photons above a threshold frequency can eject electron from the matter. We have discussed this one with a problem also. The matter such as electron also reveals wave-like behavior, and that is confirmed by the Davison-Jarmar experiment that we have discussed. Next is that de-Broglie hypothesis unifies light and matter. All particles have a wavelength, and that wavelength is given by h is equal to h by momentum p. The dual nature of both light and matter is known as wave particle duality. Quantum mechanics provides the necessary framework to explain behaviors that classical physics cannot, especially at molecule, atomic or subatomic scales. Okay. So, now with this one, and next class we will be discussing with the interaction with the matter. Thank you very much for being with me.